Dear students, in the last video, we discussed about the concepts of image segmentation. As you have seen, image segmentation, it is the process of dividing the image into its constituents. Also, we discussed about how to detect isolated points, how to detect the line in various directions, such as horizontal, vertical, and in the diagonal direction. We have used the different type of masks for detection of isolated points along with the lines. However, in this video, we are going to discuss about the next topic, that is edge detection. For edge detection, basically we use gradient and Laplacian operators. So gradient operators, they are first order derivatives. So as you know, the image is basically a two-dimensional function. The gradient of f of xy, that is the two-dimensional function, can be denoted as del f. The gradient of function f of xy can be denoted as del f and is given by this particular equation. So basically it is a column vector with two elements, gx and gy. So gx is gradient along x direction and gy is gradient along y direction. So gradient in x direction is dou f by dou x and gradient along y direction is dou f by dou y. The magnitude of this gradient function del f is given by the equation magnitude of del f. It is square root of gx square plus gy square. However, in image processing, this can be approximated simply as the sum of gx and gy. We take the absolute value of gx and absolute value of gy to have magnitude of the function f of xy, and angle of this gradient function del f can be represented as alpha of xy and is given by tan inverse of gy divided by gx. This is how to calculate alpha of xy. But however, students, for edge detection, we use three different masks. We use the pivot mask or pivot operator, Sobel's operator, along with we use Roberts cross gradient operators. So these operators, these basic gradient operators, already we have discussed in the second module under the heading of image enhancement using spatial domain techniques, right? So here again, it is just a repetition of the same concept. We are discussing about three gradient operators. They are Prewitt, Sobel, and Roberts cross gradient operators. Okay, here first we are going to start with the Prewitt mask. So this is the mask we use for calculating gradient along x direction using Prewitt mask, and this mask we use to calculate gradient along y direction. So that here, using this Prewitt mask, the gradient along x direction can be written as the difference of third row and first row. Suppose if the pixels of the image are represented as Z1, Z2, Z3 up to Z9, then Gx can be written as the last row, that is Z7, Z8 and Z9 minus Z1, Z2, Z3. The difference of third row and first row will give us the gradient along x direction. And similarly, the gradient along y direction can be written as the difference of third column and the first column. So that the gradient along y direction is simply Z3 plus Z6 plus Z9 minus Z1 plus Z4 plus Z7. This is how to calculate gradient along x direction and y direction using pivot mask. Once you calculate gx and gy, you'll be able to calculate the magnitude and the angle by using these equations. Magnitude simply it is square root of gx square plus gy square, and the angle is tan inverse of gy by gx. Similarly, the Sobel's operator or Sobel's mask is given by this particular diagram. If you look at the difference between Sobel's mask and pivot mask, the only difference is the central element. So the central element, instead of 1, we have 2. Here it is minus 2, here it is plus 2. So now to calculate Gx, the equation becomes Z7 plus 2Z8. As we have 2 as the coefficient in place of Z8, we write 2Z8 plus Z9 minus in bracket, we take again Z1, 2Z2, then Z3. As we have 2 as the coefficient in place of Z8 and Z2, here we get 2Z8 and 2Z2, right? Similarly, the GY, that is gradient along y direction, can be calculated as Z3 plus 2Z6 plus Z9. Then minus in bracket, we get Z1 to Z4, Z7. This is how to calculate Gx and Gy using Sobel's mask. Then once you calculate Gx, Gy, you'll be able to calculate the magnitude and the angle of direction. But remember, Sobel's operator, it performs better compared to the pivot mask. Then we have the third one, which we call it as Roberts cross gradient operator. So it is with only 4 elements: minus 1, 0, 0 plus 1. This is 0 minus 1 plus 1, 0. So in this case, Gx is computed as Z9 minus Z5. Gx is Z9 minus Z5, and Gy can be computed as Z8 minus Z6. While using the Roberts cross gradient operator, we consider only these 4 elements whose location will be Z5, Z6, Z8, Z9. So accordingly, we get these equations: Gx as Z9 minus Z5. This is the location of Z5 and this is location of Z9. And similarly, this is the location of Z8 and Z6. Students, this is how to find whether the pixels belongs to an edge or not. Then here we are going to look at the characteristics of first and second order derivatives. So actually for edge detection, we can make use of both the gradient and Laplacian operators, which are also known as first and second order derivatives. Here there are some characteristics of first and second order derivatives. So first order derivatives, generally they produce thicker edges in the image. If we use gradient operators, they produce the thicker edges in the image. The second order derivatives, they have stronger response to finer details. If you have very minute details, the second order derivative provides better results, such as thin lines, isolated points, and noise. There, the second order derivatives, they produce good results. Then the second order derivatives, they have one problem: they may produce double edge response at ramp and and step transition in intensity. The sign of second order derivative can be used to determine whether a transition into an edge is from light to dark or dark to light. So when we apply Laplacian operators, that is the second order derivatives for edge detection, we can make use of the sign of the result to find out whether the edge is in the region of light to dark or dark to light. So this is all about the edge detection. That is, we can segment the edges of the image. We have the next topic, what is known as edge linking. So actually, when we apply edge detection algorithms, that is when we apply gradient operators, uh, that is Sobel's mask, or maybe Roberts cross gradient operator, or even when you apply the first one, pivot mask, we will be able to detect whether the pixel belongs to an edge or not. We'll be able to detect only whether pixel belongs to the edge or not. But once such pixels are found, we should be able to group these pixels to form an edge. That is the edge linking concept. It is used to group the edge points or pixels that are detected using edge detection algorithms. So we have two methods for edge linking, that is to group the pixels belonging to the same edge. We have two methods. One is local processing, which is called as local edge linker, and we have the second method, what is known as the global edge linker. So actually for global edge linking, we use Huff transform, which is mainly used for line detection. Okay, here we'll discuss these concepts one by one. First, we are going to start with the local edge linker. So this is one of the simplest concept. Here, what we do is we are going to group the points based on some similarity criteria. Here, it includes two steps. The first step is detect the edges using some edge detection algorithm. The first step is very simple. You just detect the edges or detect the pixels whether they belong to edge or not by using edge detection algorithms. Once the pixels are detected, then we analyze the characteristics of these edge points by using a 3 by 3 or 5 by 5 mask, and we group these pixels into an edge if some criteria for similarities met. It is very simple. First, identify the pixels whether they are belonging to edge or not. Then after that, we just find out whether these pixels they have some criteria for similarity, like they may be having same color, they may be in same direction, or their magnitude may be same. Based on some criteria, we are going to identify whether the detected pixels belong to a same edge or not. This is the concept we use for local edge linker. Okay, here we have an example. Assume that you have a pixel at location x comma y, which is an edge point. And suppose if you want to know whether the pixel detected at location x naught comma y naught belongs to the same edge as that of the pixel at location x comma y, we can use a condition of this kind. The condition is you just find the difference between the magnitude of pixel at location x comma y and pixel at location x naught and y naught. If the difference of magnitude of pixel at x naught, y naught and pixel at location x comma y, if it is less than or equal to E, assume that E is some threshold value for magnitude. Okay. Along with that, if the difference between the direction of these two pixels, if it is less than or equal to some angle A, if both the conditions are met, we can group such pixels to form an edge. Please try to understand this concept, students. The concept is simple. Find the difference between the magnitude of two pixels. if it is less than or equal to some threshold value, and along with that, if their angle, the difference of these two pixel angles, if it is less than or equal to a, in that case, you group both the pixels into the same edge points. This concept we call it as local edge linking algorithm. The next, we can use one more concept called Huff transform. So basically, a line can be represented this way. So this is the xy plane we have. So in the xy plane, you will be having x-axis and y-axis, and the equation for line can be written as y dash equal to mx plus c. The basic line equation is y equal to mx plus c. Here we have written it as y dash equal to mx dash plus c. But however, in case of Huff transform, instead of xy plane, we use parameter plane or parameter space. Here what we do is we take m and c as the coordinates. We use m and c as the plane parameters. Okay, by this equation, we can write c equal to, with the basic equation y equal to mx plus c, we can write c equal to minus x dash m plus y dash. This parameter space is employed in Huff transform to detect whether the detected pixel belongs to same edge or not. We have some algorithm. We discuss the algorithm employed by Huff transform. The steps in the Huff transform algorithm are: first, we are going to divide MC space, also called as parameter space, into small divisions which are called as accumulator cell. We are going to divide the MC space. This is M and C parameter space. We are going to divide this space into small divisions which are known as accumulator cell. The accumulator cell is represented as A in bracket m comma c. For a point x dash y dash, we select one value of m and calculate the value of c using this equation c equal to minus mx dash plus y dash. In the second step, we select one value of m and calculate the values of c using this basic equation c equal to minus mx dash plus y dash. For every value of m, calculate c and subdivide a of m comma c one by one in the whole range. In the last step, the pixels whose MC values, M and C values, they belong to a same cell, they are considered as part of the same edge. Students, please try to understand the algorithm. First, we are going to divide the MC space, which is also known as parameter space, into small divisions, and these small divisions they are called as accumulator cells, as shown here. Okay. The next, what we do is, for a point x dash y dash, we select one value of m and calculate the c value using this equation c equal to minus mx dash plus y dash. For every value of m, calculate c and subdivide one by one in the entire range. The pixels whose m and c values, they belong to a single cell, they are considered as the part of the same edge. This particular concept is called as Huff transform, or it is also known as the global edge linking algorithm. Students, this is all about how edge detection is carried out. In the edge detection algorithms, we use gradient operators to detect whether pixel belongs to an edge or not. Then we discussed about edge linking algorithms. The edge linking algorithms, they are used to group the pixels belonging to the same edge. There again we have two concepts. One is local edge linking algorithm, and the second one is global edge linking algorithm. Okay, thank you students. We discuss the next topic, that is thresholding, in the next video. Thank you very much.